So when you put your cookie sheet in, it transfers the thermal energy. Instead of absorbing it, it transfers it to the food you're cooking, right? Because you don't care about the pan getting cooked. You care about your wonderful scones getting cooked. But also, when you take the pan out and leave it there for like 5 minutes, what happens? It cools down, so you can touch it again. You can wash it and not burn yourself. But your scones might stay like warm and fuzzy and creamy. Not creamy, because they're brittle.
I don't really fuzzy either.
I really want one now.
They're really good. Really.
Were there any left over?
At the coffee shop, I don't know. All I know is that Sunday crew came in and there were no scones left. So, but I will say that certain people on that coffee shop team, that particular team, tend to take more than one of pastries or like sweets.
Why did I take one?
I don't know. Some people have this thing where they're afraid to eat in front of others. Maybe that's it.
No, I was embarrassed. That's all.
I'm sorry. It's because you didn't want like a little scone.
No, it's like when people offer you water at your house and you're thirsty, but you still say no, thank you. Like you're thirsty, but you're like, no, thank you. I don't know.
I'll get it myself.
I'm not familiar with that. Okay, so alright, here's where we're at. So this X ample problem. We have 942 joules of thermal energy added to 50 grams of water at 25.1 degrees Celsius. What will its final temperature be? 942 joules would be Q. 50 grams would be M. 25.1 would be your original temperature. And then you know for water, here are the units on this. It's joules per gram degrees Celsius. So use the formula, plug in, and see if you can solve.
Wait, don't you need? Oh, you can change the heat.
Because you want to know, well, we have the heat, that's Q. We have the mass, we have CSP, and we want to find the change in temperature. I wasn't giving you that weird, giving you the weird look. I was looking out the window and I saw the base of the volleyball net, and I was like, is there a ladder out there? But it's the volleyball net. Okay, so this is how we would do this. Q equals CSP, God bless you, delta T. I'm not going to use the temperature because I want the change in temperature. So I will solve for delta T. Delta T is Q over M CSP. Q is 942, M is 50, and CSP is 4.12. Now, I'm going to check really quickly to make sure these units match the units I have. So my answer will be in degrees Celsius. I use grams and I use joules, so I'm good. Now, I will solve that out, and you get 4.51 degrees Celsius. Is that my answer? No, it did not get 21 degrees colder. This is the change in temperature. So I will add that to the original temperature. To get my new temperature, which is 29.6 degrees Celsius.
Where do you get 412 from?
Specific heat capacity of what? So, for comparison's sake, I would like you guys to do the same thing now for aluminum. I want the stripe still. So, aluminum's specific heat capacity is 0.92.
with the same stuff up there. Just
Pretend he's the teacher, make him feel like they're the teacher.
Whoa, this pencil is so nice. Writes so neatly. You guys get like 200 degrees Celsius? I'm not using a calculator, so
Can't think of what to do though.
you get 200. Plug in the same numbers with the new CSP.
Oh.
Only the students that calculate it out.
Change in time.
Temperature, buddy. Temperature.
Oh. So it's 942 times
No.
4.18.
No. It's 942 over 50 over 0.92.
952 over 50 over. What? Wait.
You're replacing 4.18 with 0.92. So a different element.
I feel like what I got is not correct.
What'd you get?
23.01.
I might be wrong.
I just 24.
Oh, I got, 20. Okay, that's better. Good thing I used pencil. It allowed me to erase.
I got 8.87 times 10 to the negative 4. I think I'm off there.
You're the teacher now.
Go ahead.
Don't teach. Or wait.
Can you teach us how to sing country songs?
I appreciate you. It's nice to see you.
Wise
You can
took
be
it
your
too far.
appreciation based too.
Wait, I wanted to be depreciated. Okay,
Appreciate
so
We can do that.
if we change the element, the only thing in this whole problem that changes is the specific key.
Oh,
So you have 942 divided by 50 divided by 0.92, which is 20.47. Huh, did it with no calculator. That was fun. Probably because you didn't fill in the joke. Your music's distracting you. I gave you a full, at least listen with the left ear pod, see, like,
At least because you're an engineer.
because you hope to gain something from this class, and
You did
it will come
computer
from the
checks.
right side. I did. I skipped your class. I kind of don't want to
You
know.
snitched on yourself.
No.
I also skipped Algebra 1 because I didn't want the heartache today.
I didn't,
I'll do it tomorrow.
I don't have anything to hide.
Alright, so this is 20.48, so 20.48, and then that gets me 45.58. Correct rounding, 45.6.
Math house exam.
So take your old temperature and you add the change in temperature.
that's what I.
Okay, if anyone has an actual question, you can raise your hand and ask. Otherwise. Okay, what did we get for water? What did we get for water?
29.6.
Okay, so aluminum, 45.6, water, 29.6. What does that tell us? With the same amount of heat added, aluminum skyrockets in temperature, water just holds that. It holds the heat. Okay? That's why, like, when you want to, like, did you guys ever do like a solar shower when you're camping? You like get the water, you fill it up in a little thing, and then you put it out. Not like that. You put it in like a clear plastic thing, and then the sun warms up the water holds it, so you can like walk away and hang it up and get like a warm water shower. Is this like new to everybody? Because the water will hold
No,
the
I don't
temperature
care.
for longer periods of time.
I have a cat.
You're like, I go to my fifth wheel trailer, or like my RV, and go in the shower, and then it has hot water at the end.
Yeah, I don't know.
All right,
Turn it off.
now, let's talk about this graph really quickly. Now, the specific heats that I've given you are only for a specific portion of this graph. Do you think that it describes this portion of the graph?
No.
Do you think it describes this portion of the graph?
Good.
Does the temperature change on this portion of the graph?
No.
No. So then obviously this doesn't work here. How about here? Most commonly, you're going to get this portion of the graph described because they give you the CSP, and then the temperature will change.
What does
Um,
CSP stand for?
Specific heat capacity. Do they give you different specific heats? I don't know. Actually, it might work for here and here. Because it's just the slope of that line, really. That's cool. All right, next X ample problem. We have a 28-gram sample of silver, and it's heated from 15 degrees Celsius to 85 degrees Celsius. And they want to know how many joules were added. So, what missing piece of information do you need, the Ryan?
Oh, we need the heat.
We are solving for Q.
Yeah.
So Q is mCSP delta T. Which piece of information are you missing?
Oh, the CSP.
Yeah, the specific heat. So then we look up silver is 0.23. Okay, go ahead and solve.
So we're finding Q in this one? Yeah.
Is it always with the 50 in parentheses? Does that stay the same?
Well, if they give you a different mass, then you use that mass.
Oh, that's nice.
Yeah, is delta T gonna be 85 or 60? No.
Well, what is the definition of delta T? Delta means
Change
in,
temperature,
okay?
70 degrees? That's not 70.
Is Q still the same?
Oh, well, they're asking for it, so
They're asking
probably
for
not.
Q.
So just multiply them. Delta T 85 or 70?
I don't know. What is the change in temperature? Some people have to process externally. It's okay. That's fine.
The change.
Change in temperature, Micah.
I don't know.
Change in temperature.
Okay.
Saying it more than once doesn't.
So the change in
Micah, How tall were you last year?
85, take away 15.
5, 9,
How tall are you this year?
change.
What is your change in height?
3 inches,
Okay.
70 degrees.
Oh gosh, he got there.
Right. That's right.
No, you got part of it.
Good job, boys.
You say
I will never be a math teacher.
You will totally be a math teacher and you're going to love it.
It's a pyramid
I
scheme.
got no problem with it.
Teach you? No, history is a pyramid scheme.
History is a pyramid scheme.
When you go into history, you're going to be a history teacher to convince other people to go into history, so they can become history teachers.
Or pastors. A lot of history people do pastoring.
That's a cop out though. So they don't want to go.
They don't want to fulfill their life potential as a history teacher, so they go into the ministry.
Yeah.
Interesting thought.
The ministry is hard. Nobody goes
Mystery?
into
What
it
is CSP?
willingly. You go into
Specific heat capacity. Ah!
Oh.
Okay. Alright, so we're solving for Q. M is 28. CSP 0.23. Change in temperature is 70 degrees Celsius. If you write your units, you'll notice that everything cancels out beautifully, and your answer is 450 joules. Rounded 2 decimal places because your data is given in 2 decimal places. Yes?
Let me make sure
How'd you get?
0.23.
I looked at the table on page 338, and then I gave it to you.
What? Why is that there?
Yeah, from the table. Yep. So things have their specific heat capacity, and that is that. Now, that's great. So this is governed by our CSP, and now that I look at my notes / the book, these are as well. Wow. I went there. But now,
But wait,
how do I deal with this part?
what part?
This part.
That's
Well, for any given substance, that is a fixed number of how much heat it takes to increase or to get 1 gram from this point to this point. There's a specific amount of heat that is required. Go get a drink. Goodbye. Because I went, wow, and you went, wow. Like, that's the thing. Okay, so this is the enthalpy of fusion. And this is the enthalpy of vaporization. Okay, so here's where it gets a little sketchy. Okay, what if we had water right here at, let's say, -10 degrees Celsius? And I said, how much heat will it take to get it all the way to this point right here, where it boils away? Then we're going to have to do a multi-stage process. I really wish I had drawn this graph somewhere else, but I didn't. So now I'm stuck with it right here in the middle of the board. So we're going to have to get the ice to melt. But before it melts, it has to be heated up to the melting point. So I have stage 1 here. Then I have to actually do the whole melting thing, right? The temperature is not going to change here, and it'll get to that point. Then, if I want to get it up to boiling point, I'm going to have to heat it up more. Once it gets to this point, I'm going to have to boil it. So it's going to have to change state now from liquid to gas to get to this point here. So let me erase some of the chicken scratch. So how do I get a sample?
You guys scared?
He just needs a little bit more time. The Price is Right reference really just knocked out. So, which equation are we going to use for phase 1? If I want to know how much heat total must be added to get from that point to this point. This equation is going to be your Q equals mCp delta T. Okay? What is delta T? That's going to be
from that point to that point.
this point to this point. If I was at -10 and I'm going to 0, it would be 10. What's CSSP for water?
4.18.
4.18. What's the mass? Let's say we have,
But you put 12.
Why?
how much do we want? Give me a random number, Micah.
25.
Okay, we have 25 grams of water. So, the amount of heat it takes to take frozen water from negative 10 degrees Celsius to 10 is right there. Multiply that out, please.
25, 4.18, not 12. Times 10. I got 1,045.
1,045 joules. And we're lost on this part because we haven't covered it, so let's jump to this part. How much energy does it take to get water from 0 degrees Celsius to 100 degrees Celsius? Well, Q equals mCSP delta T. Mass is still what?
25.
You didn't switch your ear pods. So you're gonna look away from the board for the whole
Yeah,
lesson.
switch.
At Dylan's solution.
Sorry that you don't feel like engaging.
Extra 0.
Do you have this thing? Mine will stay in my left ear, but it won't in my right ear. And I've tried all the different attachments.
Yeah, I'm like.
So it stays in your right ear. And why don't you sit here?
That's why you
Absolutely.
should just stick to the one.
No, it's fine. I'll make room for you.
Okay. CSP for water is still
4.18.
4.18. Michael, what's delta T? Going from the freshly melted water all the way to boiling? 100. So this one is
10,450.
10,450 joules. And now we're done. Just add them together, right?
No.
Wrong, because we have left out two important parts that will require energy. So let's calculate how much energy is required to get it from frozen ice, solid, to liquid. That's this part right here. Okay, so on page 337, you have a table, again, that gives you delta H for melting and boiling. So, your homework, copy all the things. So we talked about 3 tables so far, copy all of them into your notes. Yes?
Why do we need to know the amount of energy for things like that?
Suppose there is a large ice block
Why?
blocking your way to get to the store. And you go, man, how much heat do I need to melt this large ice block? But it's not enough for it to be liquid, because then it will destroy your yard and your mother's flowers
So you
in the
need to
front.
know energy in order to melt something? Why can't you just do big fire and melt?
Big fire.
Big fire.
Just
Because we want to know how much of big fire is required.
Like you melt like you. Oh, so it's like with the mixer, you don't want to put too much into it with the busters.
I mean,
because
yeah.
That makes sense. Busters.
I mean, we just want to know. We want to quantify this. So, if you're bored, you have a single ice cube, and you're like, oh, how much heat should I add to melt this? Like, you're going to do all of this work, right? So, what do I find from the table that you're copying on page 337? It says for water that delta H where am I? Of fusion is 6.01 kilojoules per mole. Ugh, these aren't nice units. So, what this is saying is that for 1 mole, remember we're not talking about temperature at all, because there is no temperature temperature change here. For 1 mole of water, Bobby's not enthused. For 1 mole of water, it takes 6.01 kilojoules of energy to go into it to get it from ice to liquid. Okay? You'll notice that to get it from liquid to the boiling point took 10 kilojoules. So, we're not surprised. What's the problem here? We can't find how much heat is required because we don't know one quantity. What don't we know? We don't know how many moles we have, right? Much like grandma's forehead. We just don't know how many there are. Okay? So, kilojoules is what I want, because that's thermal energy.
Rinse.
Yeah.
Wash your hands, come back when you're ready.
Oh wait, no, I'll be.
So, we have to convert 25 grams to moles. I have bad news. Class is over. So, your homework,
Copy the table.
Copy all the tables.
attempt to answer this problem.
That?
So, figure out how many moles you have, multiply by that. For this part, you will need the number 40.7 kilojoules per mole. That's that part. So, find out how many moles you have, multiply these two numbers by that, add them all up, and you're done. Woo! Goodbye.
Okay, we're done.
Wait a minute.